Dinosaurs did not inherit a peaceful world. They emerged on a supercontinent whose vast interior could become brutally dry, where climates shifted across immense distances, and entire ecosystems repeatedly collapsed. Pangaea connected almost every major landmass on Earth, opening migration routes without the ocean barriers that divide continents today. Yet that same geography also created extreme environments, intensified competition, and exposed life to catastrophes capable of rewriting evolution. At first, dinosaurs were not the rulers of this world. They were relatively minor animals, living beside larger, more successful competitors. Then the planet changed. Mass extinction removed dominant groups. Volcanic upheaval transformed the atmosphere, and the supercontinent began to fracture beneath their feet. So how did a group that began in the shadows become the dominant land animals of the Mesozoic? The answer begins not with dinosaurs, but with the continent that tested, scattered, and ultimately transformed them. To understand that world, we must first abandon the map we know. There was no Atlantic Ocean dividing the Americas from Europe and Africa. India had not yet collided with Asia. Australia remained attached to Antarctica. The familiar outlines of the modern continents were locked inside a far larger structure. By roughly 300 million years ago, a long sequence of continental collisions had assembled most of Earth's land into Pangaea. Its name means all Earth, but Pangaea was not simply a larger version of a modern continent. It altered the physical behavior of the planet. Today, oceans separate major land masses and influence nearly every regional climate. Water absorbs and releases heat more slowly than rock and soil. Coastal regions are therefore often protected from the most severe temperature changes experienced farther inland. Oceans also provide moisture. Currents redistribute energy. Seasonal winds carry water inland and return it to the sea. Pangaea disrupted this familiar balance. Large parts of its interior lay far from a coastline. Moisture traveling inland could be lost before reaching the deepest continental regions. Land surfaces heated and cooled rapidly. Seasonal differences could become severe. The result was not one uniform climate. Pangaea spanned many latitudes and contained mountains, river basins, coastlines, deserts, forests, and immense seasonal environments. Some regions were wet, others were dry. Conditions changed over millions of years as the continent shifted and atmospheric circulation reorganized. But its scale created a persistent problem. Life occupied a landmass so vast that environmental pressure could operate across continental distances. Evidence for that vanished world remains inside rocks, scattered across continents that are now separated by oceans. Ancient sediments preserve signs of drought, river systems, lakes, sand dunes, flooding, and repeating rainfall cycles. Across former Pangaean regions, red rocks preserve iron-rich sediments exposed to oxidizing conditions, often associated with dry terrestrial environments. These rocks do not describe a lifeless desert covering all of Pangaea. Instead, they reveal a complex world where environmental stability could never be taken for granted. In parts of Pangaea, long dry intervals were interrupted by intense seasonal rainfall. River channels shifted, lakes expanded and contracted. Habitats that supported life during one period could become hostile during another. The supercontinent behaved like a vast climate machine, and every organism living upon it was trapped inside that machine. For a species adapted to one narrow habitat, environmental change could be devastating. A dependable water source might disappear. A plant community might move. Prey could decline. Migration routes could close. Specialization could bring great success, while conditions remained stable. But when the environment changed, specialization could become a weakness. Flexible organisms had another option. They could move, alter what they ate, tolerate a broader range of temperatures, or occupy more than one type of habitat. This did not make survival easy. It simply meant that instability did not affect every lineage in the same way. Across millions of years, Pangaea repeatedly filtered life. It rewarded some strategies, punished others, and reorganized ecosystems long before dinosaurs became dominant. Yet even the harshest drought was not the greatest threat. Beneath the northern reaches of the supercontinent, geological forces were preparing an event that would push life toward the edge of collapse. Around 252 million years ago, at the boundary between the Permian and Triassic periods, Earth experienced the most severe known mass extinction in its history. The event is known as the Great Dying. Its exact sequence remains debated, but evidence points toward vast volcanic activity in what is now Siberia. This was not an eruption comparable to a single modern volcano. Magma rose through the crust over a vast region. Enormous quantities of volcanic material accumulated in repeated pulses, forming the geological province now known as the Siberian Traps. The lava itself was only part of the danger. Volcanic systems can release carbon dioxide, sulfur compounds, and other gases. Magma intruding into surrounding sediments may release still more carbon. Over time, these emissions can alter the atmosphere, disrupt the carbon cycle, and change global temperature. The environmental crisis at the end of the Permian appears to have involved several connected pressures. Rapid warming placed organisms under severe thermal stress. Warmer seawater held less oxygen. Changes in ocean circulation and chemistry further destabilized marine habitats. Acidification threatened organisms that built shells or skeletons from carbonate minerals. On land, rising temperatures and shifting rainfall damaged plant communities and freshwater systems. Food chains weakened from the bottom upward. An extinction of this scale cannot be understood as a single dramatic moment. It was a cascade. Climate affected plants. The loss of plants affected herbivores. The decline of herbivores affected predators. In the oceans, warming interacted with oxygen loss, altered chemistry, and ecological breakdown. One failure intensified another. By the time the crisis ended, entire ecosystems had vanished. The survivors entered a depleted planet. Forests did not immediately return to their former state. Food webs remained simplified. Many ecological roles were empty. Recovery unfolded unevenly over millions of years. This was the world into which the ancestors and early relatives of dinosaurs emerged. But catastrophe did not immediately crown them as rulers. The early Triassic belonged to survivors of many kinds. Some were distant relatives of mammals. Others belonged to the great reptilian lineage called the Archosaurs, a group that would eventually include crocodilians, pterosaurs, dinosaurs, and birds. These animals experimented with different bodies and different ways of living. Some became heavily built herbivores. Some occupied rivers and wetlands. Some developed armor. Others evolved into powerful terrestrial predators. The post-extinction world was not waiting for dinosaurs. It was crowded with competing possibilities. For much of the Triassic, animals on the crocodile side of the Archosaur family tree were among the most conspicuous members of terrestrial ecosystems. Some walked on 4 limbs. Others could rise onto 2. Their bodies ranged from low, armored forms to tall predators capable of attacking large prey. Alongside them lived large amphibians, herbivorous reptiles, mammal relatives, and many other groups now absent from the modern world. Dinosaurs were late arrivals within this recovery. The earliest unequivocal dinosaur fossils appear in late Triassic rocks, dating to roughly 230 million years ago, though the deeper origin of the lineage may have occurred earlier. Some of the best-known early fossils come from what is now Argentina and Brazil. These animals did not resemble the giants that dominate popular imagination. Many were relatively small and lightly built. They walked on two legs and moved through ecosystems, in which they were only one element among many. Even defining the first dinosaur is difficult. Fossils are incomplete. The earliest members of a lineage often retain characteristics shared with close relatives. A fragmentary skeleton may change its position on the evolutionary tree as new specimens are discovered or old bones are re-examined. The boundary between the first true dinosaurs and their closest dinosaur-like relatives is therefore not a clean line drawn across time. It is a transition reconstructed from scattered evidence. What the fossil record does show is that dinosaurs did not begin at the top. They were not instantly dominant. In some late Triassic environments, they remained rare and limited in diversity, particularly in certain tropical regions. Ecological instability may have prevented large herbivorous dinosaurs from becoming established for long periods. This matters because it changes the central question. The mystery is not simply how dinosaurs evolved. The mystery is how marginal animals survived within a crowded reptilian world long enough to inherit it. Part of the answer may lie in locomotion. Many early dinosaurs carried their legs beneath the body, unlike the more sprawling arrangements seen in many other reptiles. Although dinosaurs were not the only Triassic animals capable of an upright stance, placing the limbs beneath the body supports efficient forward movement, helping an animal travel farther and remain active without the body swinging heavily from side to side. But posture alone cannot explain dinosaur success. Several competing archosaurs also possessed effective locomotion. Some were larger, some were heavily protected, some occupied ecological roles that dinosaurs would not dominate until much later. There may have been other advantages. Evidence from dinosaur bones in comparison with birds suggests that air sac systems evolved within the broader dinosaur lineage. Such respiratory anatomy may have supported efficient breathing and helped manage body heat. Growth patterns preserved in bone also indicate that many dinosaurs grew differently from most living reptiles. Some achieved rapid, sustained growth, though growth rates varied widely between lineages and environments. The possibility that early dinosaurs possessed insulation or elevated metabolic activity has also received attention. Evidence from later dinosaurs and pterosaurs suggests that filament-like body coverings had deep evolutionary origins. But the appearance and distribution of insulation among the earliest dinosaurs remain subjects of research. None of these features should be treated as a magical solution. Evolution rarely depends on one trait. A useful adaptation becomes decisive only within a particular environment. Efficient movement matters when animals must travel. Rapid growth matters when reaching. Reproductive size quickly improves survival. Insulation matters when temperatures fall. Pangaea created a world where conditions differed sharply across latitude and season. A lineage able to function across a wider range of environments would possess an important advantage. But that advantage did not mean dinosaurs could move freely everywhere. Pangaea was physically connected, yet it was not ecologically open. Deserts, mountains, rivers, climate belts, and extreme seasonal conditions created invisible barriers. An animal did not need to cross an ocean to be stopped. A region too hot, too dry, or lacking. Suitable food could be as effective as a sea. Studies of late Triassic fossils suggest that climate helped control when and where early dinosaurs dispersed. Their expansion across the supercontinent was not one unstoppable wave. It occurred in stages. For generations, populations spread through suitable corridors. Some reached in new regions, others disappeared. Climate changes could open a route and later close it again. The fossil record captures only fragments of those movements. A bone preserved in Argentina and a related animal found elsewhere do not prove that one individual crossed Pangaea. They reveal that lineages expanded through populations over immense spans of time. No animal understood the journey. Each generation moved only through the world immediately around it, following water, food, shelter, and opportunity. But over millions of years, those local movements became a continental expansion. This was one of Pangaea's greatest evolutionary effects. A lineage that adapted to a new region could continue moving without confronting a major ocean. Populations could occupy environments separated by thousands of kilometers while remaining part of a connected terrestrial world. Geographic spread did not guarantee survival. It did, however, reduce dependence on a single location. A drought might destroy one population, while another survived farther north. Volcanic activity could damage one region, while distant habitats remained productive. Local competitors might be overwhelming in one ecosystem, but absent in another. Expansion, distributed risk. Pangaea became an evolutionary highway, but only for organisms capable of passing through its environmental gates. Dinosaurs slowly became one of those groups. Their fossils eventually appeared across large portions of the supercontinent. Yet for most of the Triassic, expansion did not equal domination. The crocodile-line archosaurs remained diverse and powerful. Many herbivorous roles were occupied by other reptiles and by distant mammal relatives. Large predators already controlled food webs. Dinosaurs had gained territory. They had not conquered the world. Then Pangaea entered another period of geological upheaval. By the latest Triassic, forces within Earth were stretching the supercontinent. Continental crust is divided into plates that drift slowly over the deeper mantle. Their motion is usually measured in centimeters per year. But over millions of years, they can carry oceans and continents across the planet. As Pangaea began to experience extension, fractures developed through its crust. Magma entered these weaknesses. The event produced one of Earth's largest volcanic provinces, the Central Atlantic Magmatic Province, or CAMP. Today, remnants of CAMP survive around the Atlantic, across parts of North America, South America, Africa, and Europe. Their distribution is itself evidence of the former supercontinent. Before the Atlantic opened, these volcanic rocks belonged to one enormous geological system. Around 201 million years ago, this volcanic activity overlapped with another major extinction event at the end of the Triassic. As with the end-Permian crisis, the exact causal chain remains under study. Camp eruptions and underground magma intrusions released carbon dioxide and other gases. The carbon cycle changed rapidly. Periods of warming, ocean acidification, and ecological disruption followed. The extinction was severe, but it was selective. Many groups vanished, others declined. Some survived with relatively limited losses. Among the terrestrial casualties were several archosaur lineages that had competed with dinosaurs throughout the Triassic. Large crocodile-line predators disappeared from many ecosystems. Other once successful reptile groups also suffered major losses. Dinosaurs survived. Why they survived remains one of the central scientific questions in the story of their rise. There may not be one answer. Some dinosaur populations may already have occupied high latitudes, where they experienced cold seasons and strong climatic variation. If early members of the lineage possessed insulation and relatively active metabolisms, they may have been better prepared for abrupt temperature swings than many competitors. Their upright posture may have supported movement across changing landscapes. Their geographic distribution meant that the lineage was not confined to one vulnerable region. Differences in reproduction, growth, feeding, and habitat use may also have played roles. Luck must not be ignored. Fossil lineages do not survive because evolution has selected them for future greatness. They survive because some populations endure the immediate conditions confronting them. A trait useful in one crisis may be irrelevant in another. A population may persist because it occupies the right region at the right time. Extinction is not a fair contest, and survival is not proof of universal superiority. What matters is what happened afterward. The end-Triassic crisis removed many of the animals that had prevented dinosaurs from dominating terrestrial ecosystems. Ecological roles became vacant. Large herbivore communities had to be rebuilt. Predator systems changed. Food webs reorganized. This time, dinosaurs were already widespread enough to respond. They did not need to evolve from nothing after the disaster. Multiple dinosaur lineages already existed. Their populations occupied different regions and ecological roles. As competitors vanished, dinosaurs expanded into newly available ecological openings. During the early Jurassic, they became the dominant large-bodied terrestrial vertebrates across many parts of the world. This was the decisive reversal. For tens of millions of years, dinosaurs had lived beside animals that appeared equally or more successful. They did not defeat all of those competitors through direct confrontation. Geology changed the rules. Volcanism destabilized the atmosphere. Climate reorganized ecosystems. Extinction removed established groups. The survivors entered a world with fewer rivals and more ecological space. The beginning of dinosaur dominance was therefore not a single evolutionary victory. It was an interaction between biological resilience and planetary catastrophe. And the same geological processes that helped create this opportunity were beginning to destroy the world that dinosaurs had inherited. Pangaea was breaking apart. At first, fragmentation did not resemble the sudden splitting of a solid object. Rifting was slow and irregular. The crust stretched, thinned, fractured, and subsided. Long basins formed, volcanoes erupted along weakened zones. Lakes occupied some of the developing rifts. Eventually, seawater entered the lowest regions. New oceanic crust formed as magma rose and cooled between separating continental blocks. The central Atlantic began to open. Measured across a human lifetime, the motion would have seemed insignificant. Measured across millions of years, it transformed the planet. The connected world of Pangaea became divided into northern and southern continental regions, commonly called Laurasia and Gondwana. These masses later fragmented further. North America moved away from Africa and Europe. South America eventually separated from Africa. India began a long northward journey, while Australia remained joined to Antarctica for much of the Mesozoic. The process did not happen everywhere at once. Land connections persisted in some regions while seas widened in others. Temporary corridors opened and closed. Shallow waters divided populations before becoming major oceans. For dinosaurs, the consequences were profound. During much of the Triassic, continental connection had allowed lineages to spread through suitable environments. Fragmentation reversed that pattern. Populations that once shared broad terrestrial connections became separated by rift valleys, new coastlines, seas, climate belts, and growing distances. Connections weakened, and gene flow declined. Once separated, populations faced different environments and different competitors. Natural selection continued, but it's no longer operated on one connected population. A useful trait in one region might offer no advantage elsewhere. But diets changed with available plants. Predators adapted to different prey. Body size, armor, locomotion, display, structures, and feeding mechanisms followed separate evolutionary paths. Over long periods, isolated, populations accumulated differences. Some became new species. Some produced entirely new branches of the dinosaur family tree. It is tempting to credit Pangaea's breakup for every spectacular dinosaur that followed. But the evidence does not support such a simple conclusion. Dinosaur evolution was shaped by many forces: climate, sea, level, vegetation, competition, extinction, dispersal, and gaps in the fossil record, all shaped dinosaur evolution. Continental breakup was not a switch that instantly created diversity. It altered the conditions under which diversity developed. The opening oceans created barriers. Changing coastlines produced new habitats. Continental movement shifted land masses into different climate zones. Regional ecosystems acquired distinct histories. Connection had helped dinosaurs expand. Separation encouraged populations to diverge. By the Jurassic, long-necked sauropods became dominant herbivores in many ecosystems. Their design was extraordinary. Small heads, long necks, pillar-like limbs, and respiratory systems that reduced the weight of the skeleton while supporting enormous size. Different sauropod lineages spread across the changing continents. Some evolved elongated bodies and tails. Others became more heavily built. Later groups would reach sizes unmatched by any other terrestrial animals. Predatory dinosaurs diversified beside them. Large theropods developed skulls and teeth adapted for attacking substantial prey. Their strategies were not all identical. Different lineages relied on different combinations of biting, slashing, speed, strength, and repeated attack. Smaller dinosaurs explored still more ecological roles. Some hunted small animals. Some became specialized plant eaters. Some developed feathers and increasingly bird-like bodies. The world was not becoming one uniform dinosaur empire. It was becoming a network of regional experiments. In the northern continents, armored dinosaurs developed rows of bony plates, spikes, and later heavy protective structures. Horned dinosaurs followed a separate history that eventually produced animals with elaborate skull ornamentation and powerful beaks. In southern regions, sauropods and predatory dinosaurs developed lineages distinct from many of their northern counterparts. But the borders were never perfectly sealed. Land bridges sometimes reconnected regions. Sea levels changed. Animals occasionally dispersed into new territories. Continental separation and biological exchange occurred together in shifting patterns. This is why dinosaur history cannot be reduced to one continent, producing one kind of dinosaur. The map itself kept changing. A coastline that blocked movement during one period could expose a corridor later. A continental bridge could permit dispersal and then vanish. A lineage could arise in one region, spread elsewhere, and disappear from its birthplace. The fossil record makes this story even more difficult to reconstruct. Fossilization is rare. Most organisms die without leaving a permanent trace. Rocks of the correct age may be buried, destroyed, inaccessible, or never exposed. Some regions have been studied for centuries. Others remain poorly sampled. An apparent absence of dinosaurs may represent a real ecological pattern, or it may represent missing rock. Scientists therefore compare anatomy, geological age, ancient latitude, sedimentary environment, and evolutionary relationships. Each new fossil can alter the route by which a lineage appears to have traveled. The uncertainty is not a weakness. It is part of the scientific process. Pangaea's influence emerges, not from one perfect piece of evidence, but from patterns repeated across geology and paleontology. Matching rock belts occur on continents, now divided by the Atlantic. Fossils of related terrestrial organisms appear on lands separated by modern oceans. Magnetic minerals preserve evidence that continents once occupied different latitudes and orientations. Rift basins and volcanic provinces trace the zones where the supercontinent began to separate. Dinosaur fossils record changing distributions before, during, and after that fragmentation. Together, these clues describe a planet in motion. They show why dinosaur history could never remain static. By the time dinosaurs dominated, the world supporting them had already begun transforming. Each phase of Pangaea's history presented a different evolutionary challenge. Its assembly created unprecedented scale, while its vast interior generated climatic instability. The end-Permian extinction erased older ecosystems. Triassic recovery created intense competition. Continental connection allowed dinosaurs to disperse. The end-Triassic extinction removed many rival groups. Rifting divided populations. Isolation, exchange, climate change, and time generated increasingly distinct ecosystems. Dinosaurs did not respond to these events as a single unified group. Different lineages survived, expanded, or disappeared at different times. Some remained small, others became enormous. Some spread widely, others were restricted to narrow regions. Many evolutionary experiments failed and vanished without descendants. The dinosaurs remembered today represent only part of that history. Their success was not inevitable. Had the end-Triassic extinction affected different regions more severely, another archosaur group might have remained dominant. Had climatic barriers persisted in different locations, early dinosaur dispersal might have followed another route. Had Pangaea fragmented in another sequence, populations would have been isolated under different conditions. Evolution does not move toward a planned outcome. It works with the populations that survive and the environments that remain. This is the deeper meaning of Pangaea. The supercontinent did not manufacture dinosaurs like an inventor building a machine. Instead, it created pressures, routes. It created barriers. It repeatedly changed which biological strategies were useful. Dinosaurs happened to be among the lineages capable of surviving enough of those changes to exploit what followed. Their rise began long before the first giant sauropod crossed a Jurassic floodplain. It began when earlier continental collisions assembled a world of extraordinary scale. It continued when the Permian extinction erased older ecosystems, and as small dinosaur populations navigated a world transformed by catastrophe.